Hi guys, this is Chef Jin Academy. Welcome to this channel. In this video I want to show you how to prepare a simple bar bending schedule for beams, and the type of beams you are going to be looking at are the simply supported beam with a singly reinforced reinforcement. Then we also have another example of beam 2, which is also a simply supported beam but with an extra bar at the bottom, and then a continuous beam with a cantilever overhang of 1.5. In order for you to prepare an acceptable bar bending schedule, if you are designing with either the BS code or the Euro code, your schedule format must always follow what we have in BS 4466. So I'm going to show you a typical BS 4466 and then explain how bar bending schedule format or table should look like. But before we do that, if you want to learn more about structural detailing of reinforcements and also how to prepare detailing from scratch using AutoCAD, then you can check out my video on structural detailing with AutoCAD on Udemy. Link to the course is the first link down below in the description of this video. In the course, you are going to learn how to detail all structural members such as slab, beam, column, staircase, retaining wall, shear wall, foundations such as pad footing, isolated footing, etc. So let us now look at BS 4466. So this is BS 4466. Specification for scheduling, dimensioning, bending and cutting of steel reinforcement for concrete. BS 4466. This is 1989 version. So if we go down, we are going to see a table where the code specify how the BBS, the bar bending schedule table, should looks like. So this is a typical example of a bar bending schedule table. The bar bending schedule is usually in A4 sheet. So you can see that the width of the paper is 210 millimeters, while the length of the paper is 297 millimeters, which is the size of an A4. So typically the A4 sheet the bar bending schedule should include the following. You can see the dimension of each of the blocks. So I'm not going to go into detail of this. I'm going to add this code also to this video, where you can download it. You can check the description of this video to download this code. So a typical BBS table should include the company's name, the site reference, which include the job number and the address, then the bar bending schedule, the bar schedule reference, the date it was prepared, the date you make the revisions, and then who prepared the schedule and then who checked the schedule. So what is important is what we have under the columns that we have. The first column is the members. This column can be ignored in some other situations. Then the second column is the bar mark. Then we have the type and size of rebars. So, and then we also have the number of members. If you have, let's say we have column 1 now, how many number of this same column you have in your drawings or in your details. So that's what we mean by number of members. The number of bars in each. So let's say you are treating a particular reinforcement. You are going to look at an example, but let me just explain the breakdown of this table. So number of bar in each means, let's say you have the different kind of reinforcement in a single member. So if you pick one single reinforcement, how many of that reinforcement do you have in that single member? So that's what they mean by total number of bars in each. And then the total number here is the multiplication of number of members times number of bars in each. Then the next column is the length of each bar. This length of each bar should be calculated based on the shape code of the reinforcement. The shape code of the reinforcement is defined as a 2-digit number that defines the shape of the reinforcement, and this shape code are usually labeled, different sides of the shape are labeled in A, B, C, D, and then we also have E or R. So different shape code have different shape, and then with that shape you can represent A, B, C, D there. So this is typical how your bar bending schedule table is supposed to look like. So if you scroll down, you are going to see some examples. This is for fabric reinforcement. So this is a typical example of shapes and their shape codes. So this is the shape code here. When a bar is a straight bar, the shape code of that bar is 20. When you have a bar that has a hook shape, then the shape code is 32. So different shapes and different shape code represent different shapes. So you can just go through and explore different type of reinforcement that we have and their shape code. You can see that each of these shape code or shape of reinforcement are labeled in A and B. So this A and B will allow you to give the dimension of the reinforcement. But in practice, it is not always like this. What I mean by that is the idea of the bar bending schedule is to calculate the total number of reinforcement you have in your structural details, so that you're able to quantify the reinforcement, or the surveyor will be able to effectively calculate the amount of reinforcement and put a cost to it. So by this BS 4460 standard, this is going to be a typical bar bending schedule for a beam. So you can see that this table follow the table that I showed you earlier. We have members, bar mark, type and size. Even though this one's distinguish it, then we also have number of bars in each, total number, the length of bars, and then the shape code, and then the dimension of each shape members. So this is a typical example of a bar bending schedule based on the reference of BS 4466. In this video, we are going to be using a simple format that is slightly different from what we have in BS 4466, but the idea of every bar bending schedule is to be able to quantify the reinforcement in your structural details, and then to serve as a guideline for the iron benders while they are cutting the reinforcement. So because of that, I'm going to be showing you two methods that are usually used in practice, which are simpler to what we have in the 4466. They end up giving us the same thing, but just to make the work much more easier for the engineer. So the bar bending schedule can take this form. So you see we have members just like the way we have in the first example. What we have in BS 446 is we have the bar mark, the size. Here we did not put type because we understand that the reinforcement we are using is one type. So when the reinforcement is of different type inside the same drawing, then you can put size and type, so that you'll be able to distinguish reinforcement of high yield strength and mild steel. Then this is the quantities, and then we have the length, then we have the total length, and then we have the form. This form represents the shape of the reinforcement and also the dimension of each side of the shape. You can see the dimension we are given. So this is a simpler format to what we have with the BS 446, which is also going to give us the same thing. Then another format is, you can see here what we did here based on what we have in 446 is to separate each members. That is, let's say you have 10 beams in your floor detail. You are going to do a bar bending schedule for each beams. So this is going to lead you to repetition of reinforcement, and also you are going to waste more time in creating the schedule. But using this method is less prone to error. That is, you hardly make mistake while you are using or while you are creating the bar bending schedule. If you look at this example, you can see that this is F beam 1, this is floor beam O1, this is floor beam O2, this is floor beam O3. You can see that in all the beams we have repetitions of bar reinforcement. This is bar mark O4, we have it in floor beam O1. This is bar mark O4 again in floor beam O2. This is also bar mark O4 again in floor beam O3. So there is tendency of repetition of reinforcement where you break down the bar bending schedule into members. It takes longer time and then it leads to repetition, but the advantage is that you hardly made mistake because you pick each member at a time. But another way in which we also use in practice is to combine all the beams together, because we understand that we can have the same reinforcement, the same size, the same shape in different repetitive beams. So because of that, to avoid repetition, so we combine all the we provide a single bar bending schedule sheet for all the members at a go. Example is this one. You can see that this table we are going to arrive at the same thing, but we did not include the members because we generalized the bar bending schedule for all the beams at once. So because of that, we have lesser reinforcement. Here we only have 5 reinforcement for 5 different type of reinforcement for this 3 beam detail. But if you use the first method, we have 5 different types, but because there are repetitions in different members, so we end up creating about 8 row of reinforcement. So let's say we have 10 reinforcement, you can end up with creating about 50 rows, and when you combine it together you are just having 20 rows. So this one reduce the amount of space, and then it is much more faster, but the disadvantage there is prone to error because you can easily make mistake in your additions and your subtractions. So if you are enjoying what I'm showing you, do well to subscribe to this channel. If you've not done that, you can share this video to your friends so that they can also learn from it. And you should also know that this channel is running a membership program where you can join and enjoy exclusive videos that are only available for members and other benefits. You can click on the join button just beside the subscription button on this down below. So let us looking at the first example. How do we create the bar bending schedule for beam 1? So the first thing you need to understand is how the reinforcement of beam 1 is being designed. So based on the output we have here, we have 3y16 at the bottom and we also have 2y16 at the top. In detailing of beam, we have 2 major reinforcements that we provide. We have the longitudinal reinforcement, which usually cater for the bending part of the beam, both tension and compression, and we also have the links. The links usually catered for the shear part of the beam, and then if the beam is subjected to torsion, we provide additional links to cater for the torsional effect on the beams. So therefore, in our detailing, we are going to be having a minimum of 2 reinforcements, one for the links and then one for the longitudinal reinforcement. So the detailing should be done according to the bar marks. So if you look at beam 1, for example, we have 2 different bar marks. We have bar mark O1, which represent the links reinforcement. You can see that it starts from here. Usually we denote it with a line where it starts from here using this arrow and ends here, and the total number is 22. The bar size is 10. This is how we give dimensions or designations to links in beams. We first start with the number of the links, then we talk about the type of reinforcement and size. So here the bar size is 10 mm. Then we talk about the bar marks, and then we talk about the spacing of this reinforcement. Then in terms of the longitudinal bar, what we are interested in is the number of that bar, and then the size of the bar, and then the bar marks. So for beam 1, the first bar marks we have here is bar mark O1, which is the links. So we are going to take O1 as our first reinforcement. So here we come under the members, we enter beam 1, Then the bar mark of the first reinforcement is 1. The size of that reinforcement is 10 mm. So we put 10 mm here. Then the total of this reinforcement in beam 1 is 22. So we have 22 here, so we include 22 in the total. Then how do we know the total length? The total length is calculated from the shape of the reinforcement. So this is how the reinforcement is going to, this is the shape of that reinforcement. So you measure the dimension of the reinforcement. So the vertical dimension is 400 here. The horizontal dimension is 175, and then we also have this hook shape here, which is 120 in length. So that is how we arrive at this. The horizontal dimension, even though this is not to scale, the horizontal dimension is 175 at the bottom and top. The side dimension is 400, and this is the shape of the hook. So if you add up all these numbers, remember that the hook, we have two of it, 120. So addition of all this number is going to give us the total length in mm, because these dimensions are in mm. Standard structural drawings are in millimeters if you are using the SI units. Then how do you now calculate this total? The total is calculated by multiplying the quantities times the length. So once you multiply 22 times 1390, you divide it by 1000 to convert this total to meter, because the total is usually in meters. But when you are doing your bar bending schedule, you must always make sure that your length, this length is not more than 12 meters, because 12 meters is the standard size of your rebar. It must always be less than 12 meters. When it is more than 12 meters, that means you need to cut that reinforcement and terminate it at a point where the length will not be up to 10 meters and lap it with another bar for continuity. So this is how we record bar mark 1. Then for bar mark 2, we understand that the top reinforcement and the bottom reinforcement of this beam is the same shape. The return bar is the same, the anchor bar is the same, and then the length of the horizontal is the same. You can see it's the same length. This one and this one, they are of the same length, the same size, so that's why they have the same bar mark. So here we have 2 number of it at the top, we have 3 number of it at the bottom. So that's why we have bar mark 2 for the second reinforcement. The size is 16 mm and the quantity is 5, because it's the same top reinforcement and bottom reinforcement. 2 plus 3 will give us 5, and then the total length, or the length, is calculated from the shape here. You see it forms this shape, so we just need to measure this dimension, the vertical dimension, from here to here. So practically this radius here is usually ignored. It can be ignored because it's a very small dimension. So, and then what we measured vertically is from here to the lower part of this reinforcement, 168. So the vertical dimension we covered for this radius, or this curved part. So that is why here the horizontal length is 4835, and then the anchor is 168 on both sides. So if you add up this side, this shape, you are going to have 5171, and just like the way we did for this, you multiply 5 by 5171, you have 25.82. so that is how you get the total length. So once you're done for beam 1, you now move to beam 2. You do the same thing, but if you look at beam 1 and beam 2, they are of the same length, but the only difference is beam 1 is not heavily loaded compared to beam 2. Beam 2 is much more loaded, because we have at the bottom, we have 5 reinforcement, we have 3 reinforcement, and we have 2 additional reinforcement on top of it. So you just have to do the same thing. So for beam 2, we have 3 different bars: bar mark 1, bar mark 2, we've explained that one, then bar mark 3 is just a straight bar. It's going to run from here to here. 3760. So that's why you see for beam 2 we have bar mark 1, the same size, the same dimension, the same length. Then for bar mark 2, bar mark 3 we have 2 number of it, and then the length is 3760. So you can see that using this method we are actually making repetitions, because bar mark 1 and 2 that we have for beam 1 and beam 2 is the same thing. Then if we now move to the third beam, which is the continuous beam with an overhanging cantilever of 1.5 meters, you can see that this beam we have the same bar mark 1 because the size of the links is the same. The size of the links is the same, since the width and the length of the beam, the width and depth of the beam is the same. So we have the same bar mark 1, you see 10, but now the total number is 29 here because the length is not the same. Here we have 22, we have additional 1.5 meters, which give us 7 numbers. So that's why the total number here is 29. So the same shape and size. So adding this total number together, we have 1390. So multiply by 29, you have 40.31. So and then for the longitudinal bars, we have two different bars. We have the same bar at the top reinforcement, but because this is a cantilever beam, it has a cantilever end, there's an additional reinforcement at the top. So this additional reinforcement have this shape. So this is the shape here. You measure the length and then the anchor. So if you do that, the total number of that additional bar is 316, but the bar mark is 5. While the bar mark for the longitudinal reinforcement, the longer one, the bar mark is 04. So we make the records, and at the end of the day we have our bar bending schedule. So but what is important for the quantity surveyor in this bar bending schedule, what we've done is the engineer's part. We also need to calculate the quantity of reinforcement based on this, because this shape is what the iron benders we use to cut the length of reinforcement, all these shapes. But we need to also calculate the total number so that the QS can just come to your bar bending schedule and read the total number of 10 mm reinforcement, total number of 16 mm reinforcement. But before we go into that, let me also explain the second type or the second table for bar bending schedule. So the second method, instead of us breaking it down into different members, we are just going to take the whole beams as a single entity and do the schedule. So for bar mark 1 now, we already know that we have 22 number of bar mark 1 here, we have 22 number of bar mark 1 here, and also we have 29 number of bar mark 1 here. The same size, the same shape, the same everything. So we just come here, we put bar mark 1, the size is 10 mm, the quantity is 73, the length is 1390 based on this calculation. So this quantity is going to be the addition of bar mark 1 in beam 1, in beam 2, and in beam 3. You can see this one is much more faster, but as I've said, it is prone to error. So we have 73. So and then you have a total number of the total length is quantity multiplied by length. So here we have 107.43. If you look at the first example, to calculate the total number of 10 mm, we need to add up 10 mm in beam 1, 10 mm in beam 2, 10 mm in beam 3. So addition of all of this will give us this total length here, 101.47. You can see that it is the same. So we are going to arrive at the same thing. Then we now move to bar mark 2. We have 5 number of bar mark 2 here. We have 3 at the top, 3 at the bottom, 2 at the top. And then for bar mark 2 we have also 5 number of it, 3 at the bottom, 2 at the top. And then in beam 3 we don't have any bar mark 2. So we just come here, 16 mm for bar mark 2. The quantity is 10, 5 for beam 1, 5 for beam 2. This is the shape of the bar mark and also the dimension of each side. So we end up with 5171. You multiply by the total quantity, you have 51.71 in meters. So then we do the same thing for bar mark 3, we do the same thing for bar mark 4, and finally for bar mark 5. So for the 16 mm that we have using the first method, we also add them up to get the total number of 16 mm reinforcement. So we add this number together with this number together with this number. So at the end of the day, we have 1129 for 16 mm. So based on the second method, we have 11128. It's just an approximation issue. So this is 11129, this is 11128. Then in order to calculate the weight of reinforcement, because what we actually need in the market is the tonnage or the weight in kilogram. So in that case, you need to know what we call the unit weight of reinforcement. The unit weight of reinforcement is given by the diameter squared divided by 162 if you are using kilogram per meters. So diameter squared divided by 162. So for 10 mm is going to be 10 squared divided by 162. For 16 mm is going to be 16 squared divided by 162. So this one is going to give us the unit weight of the reinforcement. Then you now multiply the same thing for the first method as well. You now multiply the unit weight by the total length to give us the total weight. So that's how we arrive at 62.61 for 10 mm and 175.82 for 16 mm. You can see that we arrive at the same thing using the second method, 62.61, 175.84. So as I've said, these are the different methods in which we prepare bar bending schedule practically. You can follow the template of what we have in BS 446s. This is the standard as prescribed, but in practice, in order to make work simpler for engineers, you can also use this method to prepare your bar bending schedule. The idea is to calculate, number one, to give the size and shape of reinforcement to help your iron benders where they are cutting the shape of reinforcement. Number two, in order to calculate the quantity of reinforcement, in order for you to quantify the reinforcement effectively with less or reduced error. This can be done like this, or you can prepare an Excel. You can prepare an Excel worksheet that is going to make it easier for you. All this multiplication can be done automatically in the Excel worksheet. You just have to input the size, the quantities, and then the calculation for the total length can be automatically calculated from these sides A, B, C, D. We just add up this side to give us the length, and then from the length you can calculate the total length down in a separate part of the Excel sheet. So this is the conventional way of doing it, but we also have a simplified method, which is this. So this is how you can generate your bar bending schedule for beams. If you want to learn more about structural detailing for all structural members, slab, beam, column, staircase, foundations, retaining wall, shear wall, etc., you can check out my course on Udemy. As I've mentioned, the link to the course is going to be the first link in the description of this video. Thank you. See you next time.